once we can start on time. Questions before we start? Anything that you want to ask? Just one of you was present in the last problem solving session. The solutions have been posted. Okay. We have the next one this week on the overlapping generations model. It will be important that you try and work on that problem. Just make sure that you understand how things work in this one. It's important. So we were looking at the case with the money supply and the population changing. Yes.
Just to ask for a level of like revision.
Sorry?
For revision for
yes.
the exam, can you
Yes.
use the past papers offline?
Sorry?
The past papers online.
Yes. What about them?
Are they still suitable to use as
Absolutely.
Yeah.
Yes, but you should first work on the module material.
Yeah.
Make sure that you're able to do all the problem sets on your own.
Yep.
And then after that, look at as many past papers as you can. Okay?
Yeah.
And the course book also, of course, a past paper. 2 halves. The second half will also be set. That will not count for your mark. But I will mark anything that's big.
No, so the summit set.
No. So there's a second.
Oh yeah.
The second element of the coursework, which will not count for your mark, but you will get requested to submit it by email to me. Anybody who does submit it by the deadline will get this marked. Anything else? All right. So we were looking at the case where the money supply and the population changes at a constant rate. Now I don't remember how much of that we've done. So what I'm going to do is briefly recap and then proceed with that. Okay. So the money supply rule is T or MT plus 1, whichever you want to write. That's not to write anything out. Okay, and the population changes according to N0 is 1. T minus 1, Z here is positive. The money supply and this population group. And the idea was that here, any change in the money supply is made effective through a lump sum tax or transfer. Okay. The way to think about that is that the change, so write an equal to sign and I'll tell you what it is. The change in the money supply from date t to t plus 1, you can work it out from there. I've done it earlier, so I'm just writing it out. Nt plus 1 minus 1 over z, and you divide that across old agents, of whom there will be n raised to the t from the population growth equation. And this will be the nominal transfer made to each agent who's old. So the real transfer will be obtained by dividing it by the price at t plus 1. Okay, we've seen this a few times. And then the budget constraints were when young, PT, consumption when young, plus any money that you carry over is less than or equal to the value of your endowment, which is Y. And when old, it's P plus 1. Consumption when you're old gets funded from the money that you carried over and the nominal value of the transfer that you receive, or less the nominal value of the tax that you pay. Okay? So when you write out the optimization problem, which I'm not going to do here, okay? So we will write this problem. If you have any questions, something that I'm skipping, tell me, and then you get substitution from the budget constraints, and then you obtain the first order condition. The first order condition would be Q1, and then this would be consumption given what you've decided to carry as money, which from your budget constraint you can work out as minus MT over PT. Consumption when old, again you get from your budget constraint MT over PT plus 1 plus AT plus 1, and then from the chain rule you get minus 1 over PT, and then similarly you get U sub 2. I'm not putting in the values of consumption because they'll be the same as what you had earlier. 1 over PT plus 1 equals 0. Is it okay? All well? Yeah? So all this wait and see. Equilibrium. Okay? Well, the total money demand is the number of young people is n raised to the t. Each of them demands a quantity of money at equilibrium prices, and the equilibrium value of the transfer that you receive. Okay? So you need to have A star T plus 1, because the money demand will depend on that, and that amount should clear the money market. That's your equilibrium condition. Okay? In other words, if I rewrite the condition here, so let me just do that. So I get from here M sub T so I need to divide here by. Please ask if something is not clear. To the E star. Similarly here I get M sub T, and here I get N raised to the T star, star, star. Similar changes there. All right? You make sure that you follow what's going on. Okay, now impose stationarity and equilibrium. I typically do it in 2 steps, but I'm doing it in this one step here. But I'll explain how it works. Okay, so then y minus C1 star will be defined mu star, which is your equilibrium real balance that you're carrying. Okay. Mu star will be MT over PT. So that is at equilibrium. Therefore, I will write it as from the equilibrium condition, capital MT divided by n raised to the t, P star t. Hence, since this is at each date, you get MT divided by n t, P star t equals plus 1 T plus 1 P star T plus 1 is equals to Z times MT T plus 1 P star T plus 1. As you said, MT and MT will cancel out. So you get P star T plus 1 P star T Okay, so now you will have inflation if Z exceeds N, and you will have deflation if Z is less than N. These are all things that I pointed out last time, if I remember right. Now the thing that we still don't know in that first order condition is the value of A star T plus 1, but that's actually pretty easy to work out. Okay. So what you want to know is what is C2 T plus 1. So this entire amount at equilibrium. So MT divided by N raised to the T star T plus 1 plus A star T plus 1. Substitute for A star from the condition that you're given there. This is MT divided by N raised to the T star T plus 1 plus, instead of A, you have N T plus 1 minus 1 over Z divided by N to the T star T plus 1. Open that out, write out all the steps. The denominator is common. This comes from the money supply rule. N raised to the T star T plus 1. Okay, but P star T plus 1 you already worked out is P star T Z over N. So you get this as, I'm going to write it here, MT plus 1 divided by N raised to the T, and then you get Z P star T something that I don't like here. Okay. I think it's okay. Yeah, it's okay. Divided by N. That is N times, Z times. These computations I strongly suggest that you do not try to memorize. You run into trouble. Just make sure you know how to do it. Okay? Otherwise, you will be in a small difficulty. And you'll see why I'm writing all this out. Just a moment. Okay. From the definition of mu. Therefore, I have everything that I need. So mu star has to satisfy the following condition. You get U1 y minus mt over ntp star, which is y minus mu star. Consumption when old, we've just worked it out. N mu star, and then you will have the price ratio, which here is Z over N. It is something that I've Z over N, and then for U2 again, here we can write it Y minus mu star. So the solution to that equation is going to give you your answer. Okay? If such a question is on the exam, and you simply write that out and work it out, of course you will get marks, but you will get a lot less than you would if you were to work it out. You need to show that you know how to do it. Okay? Please be careful. And as I said, it's a good idea to really work it out from first principles in all of these things. The approach is exactly the same. Okay? Write out your optimization problem, which I haven't over here, but I did it the last time, even for this case. Substitute or through the Lagrangian, work out the first order condition, work out what's the equilibrium condition in the money market, and then impose stationarity, impose equilibrium. You will get your value for mu star, work out consumption when old, and you get an equation in one variable. Is that all right? Anything that's not clear? All well? Okay, so for the golden rule, so that's my stationary monetary equilibrium. Once I know mu star, I can work out all the other variables. That's not a problem. So for the golden rule, your feasibility feasibility condition for the golden rule, you can work it out from the feasibility condition in general, but I'm going to write it down directly here since I don't want to spend a lot of time on it because we've done it a few times. So the problem is to maximize by choosing C2, this is what I'm typically writing it as. Okay, a non-negative quantity, u of, instead of C1, I'm going to write it as y minus C2 divided by n, and C2, the first order condition there, becomes, and it should be no surprise, this is going to be the first order condition that you will get in the case where the population changes and you don't care about the money supply. Because the golden rule is the planner's problem. It's got nothing to do with the market economy in terms of what the problem is. Okay, so Z should not appear anywhere. And therefore, the first order condition here will be 1, y, C2, GR divided by n, C2GR, I pick up, minus 1 over n, plus U2, let's write it out, 1 minus C2GR, C2GR, and 0. And you notice that you get the same first order condition provided Z equals 1. Okay, so same as that stationary monetary equilibrium, if and only if Z equals 1. Is that okay? You get the same condition. Now you might wonder about feasibility. Well, feasibility is the same in both once you impose stationarity. Okay, you check in various. All right? So why are we doing this separately? Well, the reason is this is showing you that although the economy is growing, right, n need not be 1. So the economy could be growing or contracting. Right? Even so, in order to obtain the golden rule, you should actually not change the money supply. The money supply should be constant. This is not exactly what Friedman would tell you. Friedman would tell you if the economy is growing, then the money supply should change at the rate of growth. Whether it gives you optimality or not is a separate matter, but it will certainly not give you the golden rule. Because this is an example economy. It's not to say that Friedman is always wrong or anything like that. But in this class of economies, that intuition is not correct. Okay, so now, what more can we say in terms of optimality? So I'm going to, questions, anything that you want to ask? Oh, well? Yeah?
Just a point. Feasibility versus like a project constraint, what's the difference?
Well, feasibility, there might be a way of thinking of them as related at some level, but the better way to think about it is feasibility gives you what is physically possible in the economy.
Yeah, so does the budget constraint.
No, it does not. The budget constraint tells you what is possible for you in terms of what an economist would call is value. You really don't care whether what you can afford to buy is something that you will be able to buy on the market. At those prices, you submit a demand. What you're actually able to buy has to comply with market clearing. You agree? Market clearing is the same as feasibility.
Okay.
That's the difference. It's an important difference. Is that okay?
Yeah.
Everyone? So, I think I've drawn these figures. I don't remember. Perhaps we stopped exactly at that point. Now let's. Okay, so we'll look at the stationary problem. So that's my endowment. I'm going to draw this in a manner that okay, so that point corresponds to 0 in y. Okay, so that reflects the feasibility constraint. Question?
Yeah, sorry, where's the n gone in the second, the U2?
Oh, sorry, there should be an n. Thank you. Thank you. So that's the feasibility constraint, and therefore my golden rule will be at the point of tangency. There's no z there for the moment. Is it okay? Now, my equilibrium will also be feasible, and therefore the stationary monetary equilibrium will also be on that line. Okay? Where on that line? Well, when z equals 1, as we saw by comparing those first order conditions, we will get the golden rule value. Right? Now, when z exceeds 1, something that I erased would show you that if z exceeds 1, the money supply is growing, which means you're getting a transfer. If you're getting a transfer, it means that at those prices, whatever those equilibrium prices are, at those prices, you can afford your endowment and then some more. And therefore, you must be at a point somewhere in this section with a price ratio that looks like that. Okay? So two different issues here. I've gone very quickly. Make sure you understand. It's what's going on in the background that you need to understand, not just the specifics of a particular model in terms of a particular example here with M and with N and Z, etc. So you are going to be on that line at equilibrium. You could either be there, above, or below. Take the case where you're below. You're on the line but below. Okay? Since you will also have a tangency, this being an equilibrium, it means that the budget line that you draw has to be tangent to your indifference curve, but on that line. The indifference curve below the golden rule point has to be flatter than at the golden rule point, right, by transitivity. Okay? There's a little more than that, but it's basically transitivity. And that, just as an aside, but an important aside, okay? Let me not confuse you further. Let's leave it at that. So it will be tangent, and since you're below the golden rule, you can safely say that it's going to be flatter. Okay? And if it's flatter, you notice that it tells you that you can afford to buy your endowment and a little more, which means that over here, Z must be positive, larger than 1. The money supply must be growing here. Is that okay? Similarly, on this side, Z will be less than 1. Over here, from that point, it's very easy to check, and I've done this a couple of times, so I'm not going to repeat the details unless there is a question, that the allocation where everybody gets that consumption vector forever is clearly worse than the allocation in which everybody gets that consumption vector forever. This is clear. Right? The initial old gets less here than there. Everybody else is on a higher indifference curve, so they're all better off. So the golden rule is a Pareto improvement. So that allocation cannot be Pareto optimal, provided we can show that moving to the golden rule is also feasible. And it is feasible. Because the initial old, Okay, we'll end up getting more, but you can write it out easily and check that everybody else, because of that transfer, gets the golden rule, maintains feasibility. There's no problem with it. Above the golden rule, of course, everybody who lives for 2 periods would rather go to the golden rule. But the initial old agent gets less, so they object. Okay, so the golden rule is not a Pareto improvement. More work is required to show that there is no Pareto improvement. Not just the golden rule, but no other feasible allocation can be a Pareto improvement. So Z less than 1, these are all Pareto optimal. All the way up to Z equals 1, and here this is suboptimal. Okay? So if there's a policy implication here, this I've already noted, that if you wish to obtain the golden rule, which says Z equals 1, you do not want Z to be larger than 1. Okay, if Z is larger than 1, you run into trouble in the sense that your allocation will not be pretty optimal. This is regardless of what's happening to me. Inflation, of course, depends on whether or not on the relation between Z and N. So you're basically separating these things, different things. Yeah.
So golden rule, just as an inference, that's the like sort of overall best welfare, like sort of equilibrium.
Careful, not there. Okay, go on, and then I'll correct you.
So as a policy debtor, surely you want to have a bias towards having the Z above 1 slightly, so that you had a Pareto improvement to the golden rule.
You don't have a Pareto improvement to the golden rule. You got it wrong.
You said that you
No,
would,
I said the point at which Z is less than 1
yes,
cannot be improved by the golden rule.
yes, but Z is greater than 1 would be.
Sorry?
But Z is greater than 1.
If Z is greater than 1, then going to the golden rule is a Pareto improvement.
But you're not at the golden rule when you're at Z is less than 1, which is bad.
I don't know about bad. What I'm saying is if Z is less than 1, moving to the golden rule is not a Pareto improvement because the initial old agent will obtain.
Yeah.
Right? And separately you can show that there is no allocation which will be a Pareto improvement. So if Z is less than 1, that stationary allocation, stationary monetary equilibrium allocation is Pareto. Yeah, but that does not solve your problem. You've got a question. Ask.
What's uniquely better about the golden rule then, as opposed to being at the point of Z is less than 1?
What is uniquely better about it is that all agents who live for 2 periods, if they had to choose a point on that line, they would always pick the golden rule.
Yeah.
However, you also have this pesky initial old agent,
Yeah.
right?
So surely, you, as
This
a
is
policy
showing you.
setter,
Sorry?
as a policy setter though,
Yes.
you would want to be at least slightly more towards Z is greater than 1. So then you could get back to the golden rule easier.
That is if as a policy maker, you want to ensure that everybody knows that you're a good policy maker. So you want the economy to function badly so that you can say that there's a role for a policy maker. But that's not my job.
Right. Okay.
My job is to
That's
say
being said is
what is going to happen in this economy. And I'm simply saying that if Z is larger than 1, then actually you can interfere. Okay? How is a separate matter. I'm not saying how you do it. I'm not saying you change Z. I'm saying as an allocation, anything that you get with Z larger than 1, stationary monetary equilibrium that you get with Z larger than 1, is Pareto dominated by the golden rule. So it's not Pareto optimal.
No.
While anything where Z is less than 1, such as stationary monetary equilibrium, is actually a Pareto optimal allocation.
But it's worse than the golden rule.
How can it be worse than the golden rule?
Well, that's fine.
If you can't compare it to the golden rule, you can't Pareto compare it. Because there is the initial old agent would rather not go to the golden rule. The initial old agent is getting 1.5 oranges
Yeah.
with Z less than 1. While if they go to the golden rule, they'll end up with 1 orange. Everybody else beats them up. And they say, I don't care. Pareto is these examples also clarify what Pareto means here. There are lots of people who will tell you that, infinity minus 1 is infinity, right? So
Yeah.
that would be a very loose statement, security. Don't take that seriously. So why not the golden rule? The answer is Pareto says no. That's all. You want to do that, that's fine. Don't tell me it's Pareto. Don't tell me that the golden rule will Pareto improve over a point over there. It does not.
Yeah, but if they're both Pareto optimal, then it doesn't really matter which one you choose.
Certainly, not just for the old agent.
Yeah, like I don't care.
Certainly. You might not care, that's the problem. You might not care about the old agent. Pareto optimality is not about altruism. You can apply Pareto optimality to an altruistic economy. That's what we're doing here.
Yeah.
You can. That's a separate problem altogether.
Policy
Pareto optimality simply says, as a policy setter, I care about everybody in this society.
Yeah.
And I want to make sure that any alternative has the feature that nobody objects. This is a very basic requirement. I don't even know whether it's a requirement of democracy or morality or whatever. I don't know. You can ask Trump about that. I don't know. But Pareto optimality says that if it's a Pareto improvement, you have to make sure, and you want to make sure that your alternative allocation satisfies the condition of being a Pareto improvement. It's an ethical matter,
Yeah.
which for many economists, for me, example, if you ask me, I would say that's the most basic thing that you want. Problem is there are huge numbers of Pareto optimal allocations. It's a separate matter. But if I have to choose, I do want to make sure, not to use many bias, that nobody's worse off in the alternative than that was.
But people could be significantly better off,
It makes no difference.
even if there are some people who are
Makes
worse.
no difference. What you're talking about are what are called cardinal measures. You
Yeah.
trade off how much one person is better off compared to how much someone else is worse off. Economists in general like to avoid cardinal measures. But there are proposals that use cardinal measures. I mean, Arrow's theorem, for example, which I think I mentioned once in class, but I haven't said much beyond that. You can get around Arrow's theorem if you allow for cardinal voting. This is true. It can be done, and some people do propose it. There are lots of economists that say, hey, we don't want to go that way. No.
No, it's fair. I think.
So long as you're clear about it, that
No, no,
would be your position. That's right. So long as you understand what's being said, you're right.
Yeah.
You had a question, Emil.
Oh, I was thinking of a question.
Yeah, and you don't want to ask.
I'm not, it would be a, it was less of an economics question.
Doesn't matter, go on.
It was less an economics question, mostly with the effectiveness of policymaking under these conditions.
Yeah. That's the question.
If it's pretty awful, I've said less than one, even if it's also pretty awful, I've said any policymaker in that situation, assuming they're influenced by the demographics that vote for them, is going to be less incentivized to move towards that golden rule because it's someone, or at least the older agents. They don't. Do they lose out? When we move to Z?
Which ones are we comparing now?
When we have the older and the younger agents, if you're at Z less than 1,
Yes.
the older agents are getting 1.5 apples,
Okay.
and you move to Z equals 1.
They get one.
They get one.
Yeah, so they lose.
So effectively, from a policymaker's perspective, let's say it's a democracy, if you move to the golden rule, you lose support from your older agents. So you're less
But
incentivized.
everybody else, if they could vote for you, you have a timeline here.
Yeah.
So that's a problem. Okay, if you think of the timeline very seriously here, then what you're saying is that there are only two agents alive at any given time. Maybe a tie.
Yeah.
Okay. Right. The voting has been considerably overlapping generations model. I'm not trying to say all that, some of these models are silly enough in whichever way you look at it. But we are not thinking in terms of any of that. We're simply saying that to avoid these conflicts, any counter proposal that you make has to be a Pareto improvement, which is actually, if you think about it, it's a very weak requirement. It's a minimalist requirement. Okay, over here, you look at it very in its stark manner, you sort of see that it has bite. That's the reason. Yeah. So, but you can set up what are called welfare functions and say that to maximize average utility and things. You can do all sorts of stuff. All of that's going to give you something which will eliminate all these other people. It will become golden. The point is doing that means you're using a cardinal measure. You need to understand that. You are essentially talking about comparing utilities across agents. You apply it. Okay. Having said that, you know that anything that you do with taking on the risk is usually with expected utility. And expected utility is cardinal. Okay, we use expected utility not because we like it because it's cardinal, but because it makes life a lot easier. But it is cardinal. I don't know if you learned this. Have you? You know what I'm saying? You know why? So when you write expected utility, you take the expectation of a function. And you will get the same ranking provided you take a linear transform of that function. If you take any increasing transform, which is which is what ordinarity would require. If you take any increasing transform, the references will not be maintained. Yeah.
If we have an indifference curve,
Yes.
that means we have a continuous utility function. Does that not imply
Yeah,
there
be,
is
be
cardinality?
careful. Let's eliminate that part of it, but yeah, go on.
But does that not
Because I don't think your point will have anything to do with continuity, but go on.
It does. I mean, it implies that there is continuity, it implies there is cardinality in the a measurable utility.
No.
Let's say.
No, you're absolutely wrong on that. That's very wrong. No. This is just a representation. Okay, so think of the first order condition. Right, you take any general problem. You take a utility function, you take a monotone transform of that utility function. Any function that's an increasing transform of that. You will get the same first order condition. So your choices do not depend on whether or not you take a monotone transform of the representation that you're looking at. That tells you that it's ordered. It's exactly right. Okay?
Okay.
So continuity of references, etc., which you need to ensure the existence of a utility function. It's very little to do with ordinarity, cardinality. What you have, what you're talking about is something else. I mean, I don't know what you've been taught. I'd be surprised if you've taught these things. But in order to get an expected utility representation, you need a stronger form of continuity, which is called the independence assay. That's it. That is stronger. That's true. But the continuity that you need to ensure that you get an indifference curve of this sort, that continuity has got nothing to do with cardinality.
All right.
Is that okay?
That's fine.
All good? Everyone? Yeah? Okay. So now, I've spent a lot of time on this, but it's all right because I can spend less time on the next topic. Not what I'm going to do now, but what I was going to do tomorrow. That won't be a problem. So now what we want to look at is the case where the government finances its expenditure by printing money. So far, we really haven't had a government. If you had a money supply rule, you call it a government, you don't know what it doesn't really matter. But now we're going to have a government, and government expenditure will be financed by money, in the same way as we have done so far, in terms of how the money supply changes. So again, your money supply rule will be as before, MT equals Z, MT minus 1 with its consequences. And the new thing will be government expenditure GT will be given by MT 1 minus 1 over Z, so the increase in the money supply divided by the price. Okay? So deficit financing, central bank printing money, etc. It's all, I don't need to go into institutional details because that takes us far afield. But that's pretty good. Right? What about your agent? Well, budget constraints, I don't care about these things. In the sense that as an agent. The budget constraints, as before. So, BT C1T plus NT less than or equal to BTY, BT plus 1 C2 T plus 1 less than or equal to NT. The problem is as before, so I'm writing it. Write out the problem, substitute, that also I'm not writing. You have all these in the handout, okay? And then what's my first order condition? Well, it's the same as what we had in our first model. Not in the first model, in the model where the money supply changes. Okay, but actually it's the same as, it's the same as we had in the first model. That's what was correct. So I get U1 from the budget constraint. Not clear? Ask.
It's M, sorry.
Empty. M sub T. Sorry, there's a P missing, right? No, that's okay. It is empty. That's all of it. That's not clear?
It's okay. That's fine.
Yeah? Yeah. So, my suggestion is the following. Before looking there, ask yourself, I look here because I need to get things done quickly. You shouldn't have to do anything. Ask yourself whether that makes sense and then check. So y minus mt pt mt over pt plus 1 and then pick up the minus 1 over pt plus 2 sub 2. I'm not writing out consumption values. 1 over pt plus 1 equals 0. Okay. Then we'll get our arbitrary condition. Or equilibrium. Okay. So that will be nt of prices. There are no transfers here, so the agent's behavior depends only on prices. Okay, has to be equal to the money supply. Okay, there's no population growth here. I noted that, but since I haven't specified it, that's the case. You can deal with the problem even with population growth. It doesn't add anything to it. So deal with it. Right. So then. Stationarity and equilibrium. Okay, so you will get y minus some C1 star, which you need to determine, will be mu star. Okay. Your first order condition now. After you substitute, so this will become capital NT, P star there, capital NT, P star, PT star, PT star plus 1. Not P star, but P star. Okay, and for the budget constraint, there. So you get mu star mt p star t is equilibrium mt p star t, which implies that across time this will be a constant. Much you would have guessed. The money supply is increasing, you're looking at a stationary consumption vector, it better be the case that you're going to get inflation. You do get inflation. Is it okay so far? Yeah? So I'm not writing it out. So when you get inflation, when you don't. So what's your solution now? So what do you think is going to change here? Any guesses? You don't want to guess. I've asked you not to. It's true. Okay, so let's see what changes. Right? So we'll change what we have there in a moment. But let's see what changes. This computation that I've half erased here is the one that we're going to look at. So what is it that we need? What we're going to figure out is consumption when old, at equilibrium, at a stationary monetary equilibrium. So that is MT over P star T plus 1, okay, which I can rewrite as MT over, well, P star T plus 1 is Z P star T from there, but mt over p star t is mu star, this is 1 over z. Mu star. Is that all right? So, what happens here? Instead of n times mu star, I get 1 over z mu star. For the rest of the first order condition, well, there is no n. But from that first order condition, you see that p star t plus 1 over p star t is the factor that you will get. So that's z. And then similarly over here, I get z. So my solution is given by the solution to that equation. Is that okay? I'm going quickly. This is why you need to be up to speed with the material so that you understand what's happening. Is it all right? Okay? So now you notice that the fact that a brief sort of comment here. When we introduced money, a money supply rule, when the money supply changes, initially I had said there are two ways to think about how money is introduced into the economy. One is what we saw on the board, which is through taxes and transfers. Someone was upset on the Monday morning, but taxes and transfers. I said that on the problem set, you will have to look at the case where it's an interest payment. I haven't done that on the board, but you will see it being worked out on Thursday. It'd be better if you work on it on your own first. Those are two things that we see, right? This is the third. There are no taxes and transfers. No, there are no interest payments here. So in the absence of interest payment, in the absence of taxes and transfers, well, how do you implement the change in the money supply? Why should you? How does it affect the economy? It would not, except that over here you have the government buying goods. Is that okay? So this is the third way in which a money supply rule of that form will affect the economy, and they affect the economy in entirely different ways. Interest payments have no effect, as you will check, or super neutrality. Now, notice over here, z better be larger than 1. Why? Because if z is less than 1, if z is less than 1, then the government is consuming a negative amount. Correct? So feasibility can be expanded. Any government, Rachel Reeves would love to say this. You know what? The government will start consuming negative amounts. That will release resources clearly. So private consumption can increase. But that doesn't make any sense. Right? You're giving an agent the capacity to produce endowments. You don't want to do that. And therefore, for the economics here to make sense, you need the restriction that z is larger than 1. For g to be positive, it's larger than or equal to 1. Okay? So z has to be greater than or equal to 1. So now, you see what's actually happening here. If z is larger than 1, then when you're old, your money is buying less. Right? You give up half an apple here. What you get back is less than half an apple. It's a stationary solution. In the basic case, with no population growth, you would have got back exactly what you put away. That's what the golden rule is giving you. But now you're losing out. Is that okay? Making sense? Not making, please ask. You know, it's not that we're running out of time so badly that we can't answer questions.
Nice. Let's go over it.
Okay, that's fine. Okay, so you can ask tomorrow. All right, now, so that's the condition. As I just said, when you add these two up, I'm not writing it out, you have this in the notes. If you add these two up, right, over here since z exceeds 1, you will be left with something which is less than y. You agree? Why is that? That's because the government is cornering goods. Now, we haven't said how much the government should corner, and what the government is consuming, so to speak, does not appear in the utility bucket. That makes very little difference to the analysis. We are not trying to figure out what's the optimal amount for the government to remove from the economy by printing money. That's not what we say. Our question is, how does the fact that the government prints money to buy goods affect behavior? It does not affect the budget constraints, but it affects equilibrium. This is clear. So something's going on here. Okay, so now let's try and draw a figure. Something similar to what we had there, but of course it will be a different figure. That's my 45-degree line. Since there's no population growth, it's y0. And I'm going to introduce the concept of an offer curve, which you may or may not have seen either with me or otherwise. So think about how the consumer's choices change as you change the price line. Okay? So you will get some sort of a curve there. I'm going to draw it. Now, the government is honoring a certain amount of resources. How much? Well, that depends on Z. Okay? So, I'm simply going to say there's a certain amount that the government is honoring, and I'm going to draw another feasibility constraint. It looks like that. So this is y minus little g and 0. Little g is the amount that the government is honoring. Okay? Remember, there is no other intervention in the economy. So the consumer, depending on the prices they face, will make choices given by the offer curve. Okay? So there are two intersections with that feasibility line, there and there. Each corresponds to a price ratio. The price ratio is given by the line through my endowment and the point that I've marked there. I'll mark it that way. There'll be another one through here. You're going to mark that. So there are two different rates of inflation at which the government will be able to buy the amount that it wishes to. Okay, this one is the higher rate of inflation. Of course, it might be possible that the government tries to buy too much and this line shifts so much that it does not intersect the curve. So if you try too hard by printing money, you might end up without an equilibrium. Okay, even if you do have an equilibrium, there are two of them. More importantly, neither of these two is even restricted Pareto optimum. Okay, you have to give up half an orange to the government. What's the best way to finance it? Well, you want a tangency with that line. And that you will get somewhere over there.